start recording then. So officially happy Thursday. Welcome back. I wanted to let you know that my plan is to go to our classroom tomorrow and see what's up with the tech, see if there's any way that I can make it work given the configuration that I have to do to run this class as a hybrid. And if I can get it to work, then we'll try to move back in there next week. But if I can't get it to work, we may be stuck on Zoom for however long it takes for the connections to get resolved. So I appreciate your flexibility. The show must go on, as they say. So we will make it work one way or another. You should have a formative assessment that you're working on to be due next Monday night. And in theory, you could do all of it right now. You should be able to do it even better after we finish quadratic models today. The next thing that you'll have to do is homework 3, which is not yet available, but I hope to have it available either tomorrow or Saturday. And I will send out an email as soon as that is available to you. So that way you'll have at least one weekend, hopefully two, to be able to work on that. It will be the same type of data analysis. You'll be given a data set. You'll be asked to estimate models, answer the questions, find the right numbers, interpret the results. So the usual kind of thing, just increasing in complexity as we get more familiar with the material. I think that's all that I had to say about scheduling stuff. Any questions or anything I'm forgetting that you can think of off the top of your heads? No so far? All right. Then how about I share my screen? Wouldn't that be helpful? Then you can't see each other, but you can see my lovely slides. And so, you know, it's a win. All right, so can you see my lovely slides? Maybe that should be my first question. Not yet?
No. Yes. Now I can see them.
Now we can see them. Okay, so we got a bit of a lag, but that's okay. We will make this work. And I'm going to remove my own picture so I don't have to watch myself talk. Because you know how awkward that is, right? When you're in a meeting and you're like monitoring your own face and your own things. I only do that for meetings where I need to keep my face polite and I don't trust myself to do it. Then I monitor my own face to like keep that, polite expression. But you guys get the unfiltered version. I'm not even monitoring myself right now. So we have been talking about quadratic models. The key to interpreting a quadratic coefficient correctly is to multiply it by 2. So revisiting slide 12 of lecture 6 here, the logic behind why we have to multiply the quadratic slope coefficient by 2 is because by itself it provides half of the rate of acceleration or deceleration of a linear slope for the change over time. And whenever we want to find, basically it boils down to either two things, taking the first and second derivatives of the function with respect to time, in which case the 2 in the exponent has to come down, or you can think of it in terms of a two-way interaction where one of the main effects is missing, and that's why the quadratic coefficient has to step in and do the job that it would normally do once, 2 times instead. So we looked at some examples in SAS, and we have a few more general slides to go over with these concepts. So let me pick up here on slide 15 for a minute. Things that you've heard before, but probably wouldn't hurt to hear again. So one thing to keep in mind about these kinds of polynomial change models is that the terms that create the fixed effect trajectory are hierarchical, and the terms that create the random effects are also hierarchical. So for instance, if we have just a fixed intercept in the model, no slopes for time, that fixed intercept is the expected mean across occasions. Once we add a fixed linear time slope, the intercept becomes the expected mean from the line at time 0, wherever you happen to have put that. So, pro tip, in your homework, if you find that estimates, variability, or standard errors related to your intercept are incorrect, check your centering, because you may have put time 0 in the wrong place by forgetting to center your predictor or otherwise not subtracting the correct constant. So that's my pro tip for surviving homework with the intercept. The same thing happens then when we add a quadratic effect of time. So time squared as a new predictor then makes time, its slope, also conditional on where time 0 is. So more generally in an interaction term, the main effects of the interaction become what are known as simple effects or conditional effects. and they are the expected slope of that predictor when the interacting moderating predictor is 0. Well, in this case, if we have the effect of time interacting with time, then the main effect of time, or what we call the linear slope, then is conditional on the time being 0 in the quadratic interaction term. So we looked at how the parameters of the model then change what they mean and then change what they are in terms of their estimates because they mean something different. So once we have a fixed intercept, linear time, and quadratic time in the model, the intercept and linear time are conditional on 0 and quadratic time is unconditional. It would become conditional if we had a cubic effect. Same deal with respect to the random effects. So if we have, say, a random quadratic model, then the underlying random effects are also conditional on time equals 0. So once we have random slopes for quadratic time, the random slope for linear time is specific to time 0 as well as the intercept. And of course, we have to multiply the slopes by 2. So we did the equations before, just to review the idea of these, because this type of structure you will see as common to any kind of growth model. Each term that creates the trajectory has the potential for both a fixed effect and a random effect. And in these models, random always trumps fixed. So if you have a random effect, that means you have to keep the fixed effect that goes with it, because that fixed effect serves as the center of the random effect distribution. The random effects to use, those are how far off from the fixed effect each person is. And so you need what that center is in order for that offness to make sense and not have it be directly off from 0. So the red then is used in my notation to highlight the fixed effects, blue are the random effects. So in this case, we have 3 different kinds of individual parameters that would make up this trajectory. An individual intercept formed by beta 0, individual linear time slope formed by beta 1, individual quadratic time slope formed by beta 2. And then each of these has the fixed part given by the gamma, the random part given by the u, where the first subscript has to do with which beta in the level 1 equation. That level 2 equation is 4. So that's why for beta 0, it's 0 in the first place for the fixed effect and the random effect. Predicting beta 1, it's 1 in the first place. Predicting beta 2, it's 2 in the first place. All right, and so in terms of number of occasions, in order to have this model, we would need 4 occasions at a minimum. So if we had 4 occasions, the model for the means would be, I'm going to use the word over-identified. That's next class. The idea, though, is that we're spending fewer parameters than we could. If we have 4 means, this model would use 3 fixed effects to try to recreate the 4 means, which means we have the chance to be wrong. So we'd want to test whether or not that function does a good enough job recreating those 4 means. On the variance side, though, we could not add any more. So in this case, we could have a random intercept, random linear time slope, random quadratic slope. Those would have 3 covariances among them, plus the residual. So to figure out how many slopes that you have, I have a slide on that in just a minute, but let's see, yeah, that's coming. We'll pause on that. Let me pause and say, hi, any questions so far? Got one no? See, I flipped it around. I didn't ask how we were doing. I'm trying out something new. Anything that you want to review specifically or hear again as we go back through this material? Any points of confusion that I can help with? Got one? No? Anyone else? Am I frozen? I'm not frozen. Okay. That's good. It just looks like I am. All right. I won't belabor the point. If we don't have questions, I'll view that as a good sign. But please know that you're welcome and encouraged to ask questions at any point. All right, so in terms of a process, like how would I go about this in a real data analysis? Here is the example sequence that I am following. And this sequence is based on the idea that because we're using residual maximum likelihood, we would not do any likelihood ratio tests involving parameters in the model for the means. Because when you're using REML, you have to keep the fixed effects the same across models to be compared. Otherwise, the likelihood is not on the same scale. So we started then with empty means random intercept. So you can always do that, even if you have unbalanced data. And the purpose of that model is twofold. It serves as a baseline with which we can compare more complex models to see if the terms that we had added had helped. It also is used to calculate intra-class correlation. So the average expected correlation of occasions from the same person. We know that that constant correlation is probably not going to be accurate. Occasions that are closer together may be more related, particularly if there's systematic change that shows individual differences. But it's a good jumping off point just to think about how much of the information and what we thought was a longitudinal outcome is actually between persons due to mean differences. So the intra-class correlation tells us that much. We would then add fixed linear time as a new predictor to the model, and to see if we need that, we would check the p-value that goes with it from its Wald test. So estimate divided by standard error is treated as either a t or a z. It's t if you're using denominator degrees of freedom and z if you're not. We can check that p-value because a fixed effect is unbounded. The center of it is 0, and it could be positive or negative, and so a Wald test with a symmetric sampling distribution is a reasonable thing. If we wanted to talk about effect size at step 2 for that fixed linear time slope, which variance should it have reduced? So this is the audience participation portion of the program. Question is effect size for level 1, I gave it away, level 1 time slope. Yeah, there you go, level 1, yeah. So more generally, if you put in a new predictor, it should explain variance at its level. So time is a level 1 predictor, it should explain level 1 residual variance. And that will make the level 2 random intercept variance go up as a consequence of the adjustment for how much of it is expected based on within person variability. So then a reasonable thing to do would be to ask, well, if I do have some kind of change on average, or actually even if I don't, a reasonable next step would be to see to what extent do people need their own version of that linear slope? To what extent are there individual differences in linear change? So at this step, I would add a variance of the slopes across persons and the covariance of those random time slopes with the random intercept that was already there. So we get covariances among the random effects at the same level because they pertain to the same individual. Where you start or where you end up is probably going to be related to how you change. So at that step, we would check the -2 difference in log likelihood with 2 degrees of freedom, and that would be our indication as to whether adding that random slope helped the model, and by extension, adding heterogeneity of variance and covariance over time helped the model fit the data more closely. And I have this squiggle equals here is what I would call it, maybe double tilde, is that a thing? Anyone know what squiggle equals is actually supposed to be? I use it for basically the mathematical version of ish, like 2-ish degrees of freedom is what I mean here. And it's 2-ish because of the mixture chi-square issue. So technically speaking, the likelihood ratio test should be a mixture of 1 degree of freedom and 2. If you use 2, which is what I've done here, you're a little bit conservative. So approximately equal, yeah, that's what I meant, ish. Good to know, thank you. I feel pretty solid on that. So we have 2-ish degrees of freedom, and by the way, in your homework, I'm telling you that you can just use 2 degrees of freedom. You don't have to try to do the mixture chi-square. If the only situation in which it would matter is if you're on the borderline of significance, in which case you might want to be more precise. At this stage, random linear time slope, what would I do about its effect size? How could I convey? Nothing. What if reviewer 2 wants an effect size? And they're not going to publish my paper without it. Then what? Yeah, a confidence interval I could give them. So use the fixed effect as the center of the interval, and then basically 2 times the standard deviation of the random intercept that goes with it. I could do that. Some might do an R-square, but I would not be one of them. So the idea of adding a random effect of any kind, here the specific example is a linear time slope, but more generally in multi-level models, when you add a random effect, the goal is not really to explain variance. The goal is to repartition it into a new distinct kind of error at a higher level. So we are partitioning what would have been level 1 E residual variance into a new source of between person differences at level 2, the random time slope for individual differences in change. So to me, R-squared just doesn't make sense in this context. Again, other people may disagree. So I would give confidence intervals. You might compute intercept or slope reliabilities to go with that idea. But anything you can do to convey like how big the variance is in the context of the original outcome should be a helpful thing. So then we added in step 4, fixed quadratic time slope. So we're asking whether or not the average trajectory has a nonlinear component to it, and not just any kind of nonlinear, but a specific kind. So we have to have the fixed linear time slope in the model in order to interpret the fixed slope of time squared as that new quadratic component. And if we want to talk about it as acceleration or deceleration, we have to multiply it by 2. So twice the quadratic is how the linear time slope changes per unit time. It speeds up or it slows down. And we can check our p-value on the wall test, the same as we did for the linear time slope, and we can do a pseudo R-square for the residual variance that remains after the 3 variance partitioning is set. So we had random intercept, random slope, residual as the 3 piles. We're looking at how much more of the residual variance at level 1 fixed quadratic time would have explained. Then we have random quadratic slope, and this is another likelihood ratio test. Now with degrees of freedom 3-ish, because we have the variance of the random quadratic slope as well as its covariance with the 2 other random effects that are already there. And so you could continue going up the level of complexity. You could do cubics or quartics, I think, quintics, sextics, septic. I think 7 should be septic, and I think that's a good sign that you've gone too far. If you have to use the term septic to describe your model, that's not good. It was a joke, folks. Septic? Yeah, thank you. See, I'm trying. If you have to use the term septic to describe your model, something went awry. There's my pro tip for today. So this sequence is just one way to go about it. An alternative would be to start with the most complex model that you think is plausible and see if taking things away hurts. So rather than building all the way up in these steps, it would be a reasonable thing, given the data and given your theory about change, if you wanted to say, I'm just going to start with a random quadratic model, fit that, and then see what happens if I take away the random quadratic slope variance and its covariances with the intercept and linear slope. So you could start at 5 and go back down to 4. So if there is a significant difference between 4 and 5, if taking away the random quadratic time slope variance hurts the model, then you're done, because you know you need it then. And that in turn implies that you would need everything else underneath it to support it. So if you do need a random quadratic time slope variance, you know you need the fixed quadratic slope to go with it. You know you need the random linear underneath the random quadratic, which means you need the fixed linear under the fixed quadratic, and that means you need both fixed and random intercepts. So this is just one example. This sort of building up is one way to do it. It's useful for pedagogy. In real life, you can potentially start at a different place take things away or add things to do your refinement and maybe save a few steps in your modeling process. Just remember, if you're in REML, not to use likelihood ratio tests on models that differ in their fixed effects. Okay, any questions on that or other stuff? Got some notes? Okay. I'm watching the chat as well. If questions come to you, even if I'm in the middle of a sentence, please interrupt me. It's not meant to be a monologue or a soliloquy. All right. So we did conditionality, talking about what becomes conditional on time 0 and such. We can do that. Random effects allowed by number of occasions. So this is one thing that is easy to stumble into wrong territory as a novice with these models and add things to the model that are not identified, meaning not potentially solvable. So if we have, let's say, just 2 occasions. 2 occasions is the bare minimum that it takes to qualify as longitudinal. So maybe like a pre-test, post-test design, some kind of before and after. That's very common. In terms of the information going into the analysis, like what the model is going to try to recreate, there are only 2 variances, one at each of the 2 occasions, and 1 covariance. So that means that you can only spend 3 parameters in the model for the variance because you only have 3 pieces of information with which to estimate those parameters. So in that case, what I would typically do with just 2 occasions is fit an unstructured R matrix and be done. I would just let the 2 variances be whatever they want, and I would let the covariance be whatever it wants, and I would be done. That has the benefit of not being wrong. It's not a lot of parameters because there's only 2 occasions, and it's a reasonable thing to expect the variability would differ before and after some salient event. People would probably spread themselves out to some extent if there's differential change. If you wanted to try to summarize those 2 variances and that covariance using random effects, you can only have an intercept. So if you put an intercept in the G matrix at level 2, your R matrix could be homogeneous, and then you would only be spending 2 parameters out of 3, or your R matrix could be heterogeneous. Each of these E residual variances could differ across occasions, in which case you'd be spending all 3 parameters. So a random intercept with differential residual variance pre-test and post-test, that would be 3 parameters, and it should perfectly recreate the original variances and covariances. So it wouldn't make a lot of sense to do that. But what you can't do in this situation is have both E variance at level 1 and random slope variance at level 2, because then you would be estimating 4 parameters, because it would take, and it's shown in the next row here, it would take intercept variance, slope variance, the covariance, so that puts you at 3, plus the residual variance at level 1 would put you at 4, whereas if you only have 2 occasion data, there's only 3 pieces of information. In general, you cannot estimate more parameters than you have pieces of information with which to estimate them. In structural equation modeling class, we call this identification. The situation in which you are trying to estimate more than what is logically possible is called under-identified or not identified, meaning it isn't going to work. So the software, I have learned, doesn't always tell you this. So in SAS, what would happen if I tried to put a random slope in here is that it would either shut off that random slope and constrain it to 0, or it would try to shut off the residual variance and constrain it to 0, and it would throw error messages saying, this isn't going to work. There's too many parameters here that you're trying to estimate. I did see in R, though, using, I can't remember whether it was LME or LME-R, I saw someone estimate a 2 occasion model that had a random slope in it, and it came out with numbers and no indication that something was wrong. So that really freaked me out when I saw that. So just because your software gives you numbers doesn't necessarily mean that you should trust them. You should always think about, what am I asking it to do, and is that reasonable given how many occasions I have, how much data I have going in. So if I have only 2 occasions, then an unstructured matrix fits just fine. I would call that a multivariate model, where I'm thinking about like occasion 1 and occasion 2 as two distinct multivariate outcomes that just happen to be on the same scale in terms of the outcome itself. Or you could put a random intercept in, but then you have the potential of asking whether the e's still need to have differential variance. You can't have a random slope that allows differential variance when you only have two occasions. It's not separable from measurement error at level 1. If you have 3 occasions, then we have 6 pieces of information going into the story, 3 variances, 3 covariances. Then you can have a random intercept and some kind of random linear slope along with its covariance. That would give you 3 parameters plus residual variance at level 1 would give you 4. Now in this case, if you let each of these e's have its own variance at a different occasion, then you would be spending 6 parameters matches your 6 pieces of information, and so that would fit equivalent to unstructured as well. So it would just be a rearrangement of the data, not a recreation or savings in terms of the numbers of parameters. So if you have 3 occasions, you can have an intercept and a slope be random, but not 2 slopes. If we have 4 occasions, then we have enough information to estimate 2 separate slopes related to time. So this could be a linear time slope and a quadratic time slope, or it could be 2 other kinds of slopes related to time, which like a piecewise model, which is where we're headed next. But you can have 2 in that case if you have 4 occasions. Let me think. You would not, I think you would still be at unstructured territory if you let the e's have different variance across time, but that's going to be competing with what the random slopes are trying to do in terms of reproducing heterogeneity. So any questions about this idea that the number of occasions you have logically constrains the number of slopes related to change over time that you can have? No question. All right. One person has no questions. That's good to know. All right, moving on. I showed you these formulas in the example, but just to make the point again, when you add random slopes for time, what you are doing behind the scenes is introducing heterogeneity of variance and covariance over time in a particular pattern. And it's a function of time squared, as well as the covariance when we're talking about a random linear time model. It's a function of time to the 4th, and all of the other terms here if you're talking random quadratic, and it gets even uglier the more random slopes you would have, like if you had a random cubic. I hope not. So this is the big picture, is that random slopes introduce variance heterogeneity. Random intercepts introduce only constant dependency, but it does not introduce heterogeneity, just homogeneity of variance. Few rules to go by in terms of how to build these sorts of polynomial models. So we've talked about most of this, but just to make sure that I've hit everything that I wanted to say. On each side, there is a conditionality of higher order terms need the lower order terms to go with them. So if I have a fixed linear slope, that presupposes I have a fixed intercept. If I have a fixed quadratic, that presupposes I have fixed linear. And on the random side, the same is true. If I have random quadratic, then I need random linear underneath it, and then I would need random intercept underneath that. There may be exceptions for certain circumstances in which there's literally no variance at a particular point, but those would be rare. And I think the conservative thing to do would be to make sure that you have all of the underlying terms that would support the correct interpretation of the higher terms. If you have a non-significant fixed slope of any kind, that does not constrain you from testing random. You can have no change on average, but still have individual differences in change. So if the fixed slope itself is not significant, you could still ask for whether that slope shows individual differences by adding a random effect. And then a little bit about the language. The way that I talk about it is the highest order term on each side. So if it's random quadratic, that implies all the lower order terms. If I had something like fixed quadratic on the fixed side, but only random linear, then I would call it that to differentiate those. It's often helpful to give an equation. Not all journals want the space for that, but you can always throw it into an appendix or supplemental material or something like that. One caution, though, is about the interpretation of the intercept and slope, which the correlations between the random effects are going to depend on the centering of time. So let's say that I have a random linear model, which would imply differential growth trajectories that look like this. So people are increasing at different rates. And the question is, where do I want my intercept? Because that dictates what the covariance between the intercept and the linear time slope actually means. So if I put it in the middle, then there would be basically no correlation between the intercept, because everybody's at about the same spot, and their subsequent rates of change. If I put it towards the beginning, then the correlation between the intercept and the time slope would be perfectly negative, because the people who are at the top are the ones that are growing the slowest throughout the study. If I put the intercept towards the end, then I have the exact opposite conclusion. The people who end up at the top are the people who change the most during the study. So none of these correlations is more correct than another, but it does illustrate that you can't just talk about the covariance without considering where time zero is, because it's the intercept at that point. The same is true in talking about how the linear and quadratic time slopes are related to each other and their covariance in the level 2G matrix. So I have 3 different ways of centering time at the top of this slide 24. I have it centered at the first occasion, in which case the linear and quadratic slope variables that go into the model as predictors would look like this. And I have it centered at the last occasion in the second spot, or centered at the mean. So I have then the linear slope on the x-axis down here, the quadratic slope variable on the y-axis, and then lines drawn through to illustrate each of these things. So they would be almost perfectly positively correlated if you're talking about sessions centered at 1. They would be perfectly negatively correlated if you're talking about sessions centered at the end instead. Or if you centered it at the mean, that's when the correlation would be the lowest. So in certain longitudinal books, particularly those written from a more statistical or biostat perspective, they may recommend mean centering time as a way to reduce the collinearity between linear and quadratic time as 2 variables, because something and something squared are going to be related. And that's all well and good, but then where is your intercept for in this last occasion, in this last scenario here? If you look at where time 0 is, it's not even a choice. Time 0 would correspond to like session 3.5. So you would end up with less correlated linear and quadratic slopes, but potentially at the expense of interpretability as to what your intercept means. So to me, that's not a good trade-off. You may also see people try to recommend orthogonal polynomial contrasts to try and reduce collinearity, but those are pretty much impossible to interpret, at least for us mere mortals. So I don't like those either. I just wanted to give this to you as a caution, like when you enter a predictor and the predictor squared, they're going to be related. So just watch out for their random effects correlation, trying to go out of bounds. So if it hits the boundary of 1 or -1, then you might potentially think about reconfiguring the model to solve that problem. But it shouldn't hurt anything too much. It's only when variances go to 0 that you really start to see estimation problems. All right, yeah, there we go. We're at the intermediate summary already. So big picture of this unit, which is going to take us a few weeks to get through. In the model for the means, the goal is to describe what the average trajectory looks like, averaging across people. And the fixed effects in the model are what create that average trajectory. So what kind of trajectory do the means show is the first thing I would want to know. And then think about, like theoretically, what kind of process is responsible for change, and how do I operationalize that process given this pattern of mean change? So the trajectory is eventually going to try to fit itself through those means. Knowing what the means are ahead of time helps you try to figure out which family of models is going to be most useful. Then on the random side, they're answering substantive questions about which aspects of change show individual differences. But at the same time, they are then allowing heterogeneity of variance and covariance over time in a way that hopefully better matches what's happening in the original data. So what we've seen so far are polynomial models, meaning time squared, time to the third. There are other families of models that we are going to explore as alternatives and actually fit them to the same data. Since these data are real, I don't know what the correct answer would be. All right, let me exit out of that for a second because there's one more slide that I need to do at the beginning of it, and then we can look at the handout. So, how are we doing? Going back to my original. Thumbs up. Anything that you want to ask about or have me describe again? Or is there anything that in your lives of analyzing your own data that this is making you think about? Because that is the eventual goal, is to get you being able to analyze your own data that are meaningful to you. Okie dokie. Then I have for you a slide that I put at the beginning because it doesn't just talk about polynomial models, it talks about any model. And now I'm going to show you how to do this. So slide 10 that I have here, I've labeled bonus because this is not in my textbook. This is something that I found after the book was written and published, and it's something that I will be adding to the second edition that I'm theoretically writing right now, even though I haven't gotten very far. The idea of how you go about testing absolute model fit when you're using residual maximum likelihood instead of regular flavor maximum likelihood. So in regular flavor maximum likelihood, we could do any kind of likelihood ratio test we want on a nested model. We could compare, saturated means unstructured to, random quadratic, where the models differ both in their fixed effects and in their random effects, and if we were in regular flavor maximum likelihood, that would be totally fine. And in fact, if you estimate these types of growth curve models using structural equation modeling software, that is essentially what the tests of model fit and all of the fit indices would tell you. Relative to the saturated means unstructured model, how close is yours? Where non-significance is desirable, because non-significance means there's no difference between what your model says the means, variances, and covariances should look like versus what the data say they want them to be. So the trick then is to figure out, okay, how do I answer those same kinds of questions when I'm using residual maximum likelihood instead? And I found this idea in another person's textbook. So Walt Stroop was one of my colleagues in the stat department at the University of Nebraska. He has a very good generalized linear mixed models book. It is a difficult book to read in parts because he does not shy away from the technical material, but he has a whole bunch of SAS code online that helps to make all of the things he's talking about a lot more tangible. So I would recommend that book for those of you who expect to do longitudinal models on binary, ordinal, nominal, count type outcomes, that kind of stuff. And I think we'll have an example or two of that in the advanced class as well. But anywho, he's figured out how to, it's called generalized linear mixed models. So there's a link to it right here in the slides. I think I linked to the Routledge site since that's who publishes it. And I have a copy, actually I think we have 2 copies in our house because Jonathan had a copy too. So I can bring that in if you're interested in borrowing it. So his approach is to tackle the 2 sides of the model separately. So there's 2 questions then. To what extent do the fixed time slopes adequately recreate the saturated means? So I asked this question of you in homework 2, and in that homework, one of the choices for your estimation was indeed regular flavor maximum likelihood, which means you could do a likelihood ratio test to answer that question. So what I want to show you is if you're not in ML, if you're using REML instead, what can you do? And the answer is essentially saturate the rest of the means. We're going to add parameters to fill up all of the ones that we didn't spend and see if they help. Because if they help, that means our model is not doing a good enough job at reproducing the means yet. On the variance side, we would hold the fixed effects constant and compare an unstructured model to the random effects best version that we came up with. And then we have just a regular likelihood ratio test to see if there's a difference, where again, a difference is bad. Difference means the model doesn't fit. Difference means you have not adequately recreated the means, variances, and covariances yet. This idea is only possible to do, by the way, in balanced data, where there is a set of right answers to come back to. In balanced data, there are only so many means to be captured across time. There are only so many variances and only so many covariances. So this isn't possible if each person has their own set of time occasions, in which case there's not a single summary of all the means or all the variances and covariances that you can come back to. So I skipped this earlier because I knew that we weren't going to get there in terms of the example for quite a while, but now we're ready to see it. So let me find example 6a. There we are, where we looked at quadratic stuff last time. So I'm on page 9 just to point out this box. This box right here on page 9, this is going to be very helpful when you're doing your homework, because I will ask questions like, what is the model predicted intercept at this occasion? What is the model predicted slope? And I ask these questions on your next formative assessment as well. This is how you find the answers. So for the linear slope, it's twice the quadratic and the time variable that you want the linear slope for. That's what goes into this box here. So I know we talked about this last time. Are there any questions on this as an idea, like how the model tells you what the predicted outcome is at a given occasion, or the predicted linear time slope? One no. You'll get a chance to see. So low stakes formative assessment to practice this first, and then moderately higher stakes homework. But again, each question being worth a fraction of a point, so it's not really that high of a stake. Just to point out that box though, because that box will help, hopefully will help you. So we did all this stuff. We did random quadratic. And we asked at the very end of it whether we were done, in the sense of whether we could add anything to the R matrix. So based on the pattern of the means and the pattern of the variances, I didn't think that adding cubic trends would help the model, and I couldn't come up with a theoretical reason why I would expect change to slow down and then speed back up again, which is what would be required from a cubic model. But I could test whether or not the residuals have any relationship left over after controlling for the random effects. So I believe the last model we looked at on Tuesday was whether or not adding an autoregressive correlation to the level 1 E residuals specifically helps the model. And that is built into all 3 of the software packages as an option. It's a reasonable thing to ask if occasions that are closer together have any additional relationship, even after you control for individual differences and change via the level 2 G matrix. Survey said the new autoregressive correlation had a parameter estimate of 0.17. So the residuals that are 1 unit in time apart were expected to be correlated 0.17. It would be 0.17 squared for 2 units in time apart, 0.17 to the 3rd power for 3 units in time apart, etc. The Wald test for that new parameter says no. I can get converging evidence using a likelihood ratio test, since this is a variance model parameter. Also no. P-values are off a little bit because these are 2 different ways of asking the same question, but they converge onto the same answer that this doesn't help. So then last time we started doing some, what I think is actually called by other folks visual analysis. We're staring at a picture. And I asked you how well you thought the quadratic model fit the saturated means. Do you remember this? Maybe? So what do you think? The saturated means are the black squares. The quadratic model is the line given by the diamonds here. Think it's good enough? This is an opinion question. You can't be wrong.
Lisa,
Yeah.
I think that the quadratic option, well, we have some differences
Hmm.
across sessions, but I think that it is good enough if you are looking for an easy option. But yeah, I would say so.
Yeah, I think it's pretty
Good
good.
enough.
Yeah, good
Yeah.
enough. There's a phrase, good enough for government work. Have you heard that before? It basically means like that's like for a standard of having things be, moving but not perfect. Like this is good enough. And so good enough for government work. Since I am a government employee, that seems appropriate. But yeah, I would say the only criticism based on this picture is it seems unreasonable that the right hand side of the U would exist, right? If we kept measuring these people, that's probably not what would happen, but we don't have the data for it. So, from the perspective of how well does this model fit the data that we have, the means that are recreated by the fixed intercept, fixed linear time slope, and fixed quadratic time slope, spending those three parameters does a pretty good job of recapturing what those six means were. Now, in a minute, we'll do a test for it, but just visually, this looks okay. We do know, based on this visual analysis plus the results of what we've seen already, that fixed quadratic does a better job than fixed linear, because the addition of the quadratic slope, the significance test for it, answers that question. If linear were sufficient, adding quadratic slope for time squared would not contribute to the model. It did contribute, and we can see that it looks like it's doing a better job, in particular at the beginning as well as at the end. And then so there's some offnesses in drawing a straight line in the middle too. Same idea for the variances. The correct answer is given by the unstructured variance. That's the black squares again. And the random quadratic model is the diamonds. So I don't have a picture for all the covariances, but the same idea, we could make pictures for how well they match. I do know that random quadratic works better than random linear based on the hypothesis test comparing those two. What I don't yet know is whether it's good enough. Looks like it's not bad, but yeah. And I don't have any pictures for the covariances, so we'd have to look at those two. So that's the last thing that we have to do, is answer that question: is the quadratic model good enough to recreate the original means, variances, and covariances over time? It's the best version within the polynomial family that we could come up with, but we don't know if it's good enough yet. Question. Carl, hit me.
Yeah, could we go back to the plot
Mhm.
for the predicted mean by session?
Yes.
One we were just on page 16.
Okay.
Sorry for the. Oh, it's just a little bit of a lag. Sorry. Yeah. So the mean. So the instantaneous time slope
Mhm.
on the quadratic model at time 0, is that slope, like, I don't know, just to go back on this terminology, like pretty close to the slope between time 0 and time 1, or session 1 and session 2 on unstructured means model?
I'm not exactly sure what you're asking yet. Keep talking, please.
Okay, so the line which is the instantaneous time slope at session 1.
Yeah, I don't have that line on here, but it would be right here.
Random quadratic.
Mhm.
Yeah, right. Yeah, it's not depicted, but if we were to draw it, would it be pretty close to the slope between session 1 and session 2?
Ah.
The saturated means unstructured variance model?
It would not. So the linear slope at session 0, it's not between 1 and 2. It's literally at session 1, which is the time 0. It's at that point, because the second it moves off, it starts changing according to the quadratic fixed effect in the model.
Okay.
So it's the slope at a point.
Calculus.
Yeah, I mean, it's like the shape of it would be the same, But it's the slope at that point. It's the slope of the line that's tangent to the curve at a particular point, which is why they call it instantaneous, because it's not between 1 and 2.
Right. Okay. Got it.
Yeah,
All right,
it's
thank you.
yeah, it's a weird concept because you can't have a slope at a point, except you can. The idea of between 1 and 2 is actually going to be operationalized in the piecewise models that are next, much more directly. So thank you for the question. Did I answer it sufficiently?
Oh yeah, definitely.
Okay. Okay. Yes, instantaneous. That's the key word here. It's weird. I give you that. And you probably remember your calculus much better than I do. Any other questions before we look at testing fit? Okay. So now we get to use a portion of the new predictor variables that I created in this example that we haven't used yet. So I am introducing into the model code, this is the top of page 17 where I am, these 3 new predictors labeled S1, S2, and S3. What these are dummy coded indicator variables where it is 1 if it's that session and 0 if it's not. So S1 is 1 if we're talking about session 1 and 0 otherwise. S2 is 1 if we're talking about session 2 and 0 otherwise, and so on. I made all 6 of them. So the logic here is how many means do we have to recreate in this data set? So this is another audience participation question here. You can show me your fingers, or you can type, or you can talk. How many means are we trying to recreate with this model over time? Yeah, 6. How many occasions are there? Is what I should have said more directly, but we're trying to make the connections here. So there's 6 means. Therefore, how many fixed effects would it take to fully capture all of those means? Five slopes plus an intercept, right? So that would be 6 in total. So if I put in 6 fixed effects, then I should perfectly reproduce the 6 means. 5 slopes, 1 intercept is how I would do it in saturated means, for instance. Okay, with me so far? Okay, so with just the polynomial part of the model, how many fixed effects have I spent out of my 6? So the quadratic growth model has spent how many? 2 slopes plus 1 more that's not written in the code explicitly but always shows up in the model. What's the 1 fixed effect that's in here too? I always put a 1 for it in the R syntax to remind myself that it's there. Yeah, intercept. So if I count, I have 6 means. I have spent 1, 2, 3 fixed intercept, fixed linear, fixed quadratic to recreate those 6 means. How many more parameters would it take to get all the way up to the 6? 3. That's why these are here. What I have done is add 3 new fixed effects that are essentially going to fill in the holes between what the actual means are and what the growth trajectory from quadratic time predicts. And I know how many I need because I know how many means I have in total. So in this case, because I already spent 3 fixed effects, fixed intercept, fixed linear, fixed quadratic, I need 3 dummy codes to fill in all the holes to get me up to 6. If I had stopped at linear time, how many dummy codes would I need instead? If all I had was fixed intercept and fixed linear, then how many would I need to get up to saturated? Yeah, 4. So it's a data-specific problem, how many more fixed effects you would need to add to saturate the model, but that's the idea, is that we're filling in all the holes, and we're going to do a joint test as to whether those dummy-coded hole filler variables have an effect. If they do, then our model's not good enough. Question, Vladimir.
So, so in this case, if you are using those dummy new variables, what is the interpretation for the first two? Because to me, the regular time in the first place, that is trying to capture the linear mean rate of change at time zero, while time times time is trying to capture the half the rate of acceleration or deceleration. So what's the interpretation of those all of those terms now?
The short answer is nothing that we care about. Because adding the dummy codes is going to mess up everything in terms of what the other slopes mean. But the purpose of adding them is to see if they help. Because if plugging in the holes helps, then you have some big holes to fill in. If plugging in the holes with these dummy codes doesn't help, then your model is good enough. And I knew someone was going to answer that question, and so in just a minute I will show you that if I put in S4, S5, and S6 instead, you get the same exact conclusion. It doesn't matter in this case which occasion dummy codes you put in, it matters how many you put in this model, because each part of it is unsaturated. That will change in the piecewise models, but for now it doesn't matter. So I added these new dummy codes in as fixed effects only. I'm keeping the random quadratic time model the same. So now I can compare directly using a test for these three new terms whether they add anything to my previously best random quadratic model. So S1, S2, and S3 go here. In the Stata code, they go here with the C dot prefix indicating that I'm treating them as continuous predictors. And in R, I'm still in Elmer. Looks like my spacing got off. Sorry, that's one of my things. I like my code to be aligned. I'm kind of nuts that way. And there they are, inside the fixed effects there. One more piece that I have to ask for, which you may or may not have seen before in code. If you've had a class from me, I'm certain you've seen this before. The idea of lumping these contrasts together to get a joint significance test. Because the purpose is, do I need these three things to fill in my holes, or is my model good enough? I need to test all three of them at the same time to answer that question. So I do that via contrast in SAS, via test in Stata, and via contest MD in R. So highlighting all three of those that do the same thing at the same time. So the way that it works is that you list the slopes that you want to test, and you give them a 1 as a multiplier, meaning I'd like one of these, and one of these. So in SAS, you list the slope, you list a 1 after it, and then you separate the degrees of freedom for the test with a comma. So the fact that in contrast in the SAS code I have 2 commas means that it understands that I want a test of 3 slopes, and that is a 3 slope test, not that I'm adding them together or subtracting them or anything like that. In Stata, the parentheses then give you the numerator degrees of freedom, and it's explicit that you're asking, hey, what if this slope were 0? And what if this slope were 0? And what if that slope were 0? And we put all 3 together, and we say, what if all 3 were 0? And you get an F test for that. So anytime you're testing more than one slope, you can ask for an F or a chi-square. The difference is whether or not you're referring to denominator degrees of freedom to get yourself a p-value. F times numerator degrees of freedom is chi-square. So the test statistics have a direct one-to-one relationship. In Stata, the keyword small turns it into an F rather than a chi-square. In contrast, in SAS, you get F by default, and I asked for the chi-square to go with it. And in R, I think because of the rest of the context of the model, it should show up as an F, but it's contest MD instead of 1D. Presumably the M means multidimensional, not I'm an MD doctor. And we have to refer to, in R, all of the fixed effects. So we have this C dot thing here, This says, I'd like a test of S1, please, because in the order of the fixed effects, that's where S1 is. So here, there's your order. So I need S1, S2, and S3, and I need each of those to be considered its own thing. Not a linear combination, but a separate slope just grouped together. Okay, so I know that might be a new idea or a new way of asking for it. It's not a new idea. So if you've seen, like in design of experiments or any other class that covers ANOVA models, the idea of an omnibus main effect of something, where it takes multiple slopes to describe the role of a categorical predictor, that's this. If you do hierarchical regression, where you enter a set of predictors in a block, and you want to know if the block helps the model, and if the change in the R-square attributable to the new slopes in the block is significant, then that test of that change in R-square, that f-test, that's this too. So it's a much more general procedure of lumping slopes together to create a joint test that corresponds to a specific research question. The question I'm asking is, do I have any holes between what my quadratic slopes say the mean should be and what the actual means are? And if so, this test will show up as significant. Okay, how are we doing? One thumb. Survey says, so yes, to your point, Vladimir, the coefficients of the original part of the model are completely different. Just don't even try to interpret them would be my answer. Like I don't know how to even think about this because it's after controlling for whether it's sessions 1, 2, or 3, which means I think this is focusing on the 4, 5, and 6 part of the model predominantly. The reason to do this output is this test right here. So this is the result of the contrast or the test in Stata or the contest MD in R, and it's lumping together my 3 slopes. The chi-square for those 3 slopes is 9. If I take 9 divided by 3, that's where I get my f. And either way, it's significant. Wah, wah. So it says, according to this, that the contribution of the 3 new dummy codes is significant, meaning there was enough of a hole to fill by them that the quadratic model is not doing a good enough job at recreating the means. Well, what about the variances? So here is the means again, 4, 5, and 6 as promised. I stuck in instead of 1, 2, and 3. Exact same set of code otherwise, and exact same result. It doesn't matter which 3 you put in, just 3, because you have to get up to 6. On the variance side then, so I'm doing a new model as a point of comparison against my random quadratic model, in which I keep the fixed effects the same. So this is fixed quadratic, and I'm having to go to GLS and R, which is why it looks a little bit different. So I'm keeping the fixed quadratic part the same. And instead of having random quadratic slopes and random intercepts and random linears, I'm switching to an unstructured matrix. So it's repeated unstructured, residuals unstructured, and I had to switch to GLS and R to do this. So it takes the correlation option and the weights option to get the unstructured matrix in R. So this then obeys the rules of Rimmel. It holds the fixed effects constant. So I'm comparing fixed quadratic either way, and I'm asking saturated model is the next class, unstructured model versus random quadratic. So the question I'm asking by this comparison then is, does my random intercept, random linear, random quadratic, all their covariances and the residual variance, do those parameters do a good enough job at recreating the unstructured variances and covariances? That's my question. So I have a difference between models of 14 degrees of freedom. That is how many more things I could have added to my model for the variance. And the p-value that goes with the model comparison is highly significant. So yeah, this isn't good enough. So the end result would be, well, this isn't really good enough yet, but it doesn't make sense to add a cubic or a quartic or go up to septic or any of that stuff. So my conclusion would be maybe I need a different kind of model. Like this family of linear and quadratic and cubic can only get you so far. If it doesn't look like that's going to work, then we need to go back to something else. So that sets us up for the other examples using the same data set of looking at piecewise models, exponential models, and then had a trick mixed into making an exponential model by logging time. So that's where we're headed next. Is that surprising that it's significant? Not really. It's kind of a lot to ask that we could have a model that fits that well with that few parameters. Keep in mind that your sample size is also going to contribute to this. So the more people you have, the more power you have to detect differences between what the best fit is and what your model says it should be. So there's the same sorts of issues with significance tests, but this at least gives you a way to answer that question. When you have balanced data, are we there yet? Not just does everything we add help, but is the model good enough yet to be used? Sadly, the answer is no. All right. Questions on code, logic, or anything else about absolute fit?
I have one, Lisa.
Yeah.
In the case of the word test, the interpretation is the same than we using likelihood ratio test. We can have more better, not better, worse, not worse models.
Yes, yes.
Okay.
So I would say that if you're talking about adding things, the model is either better or not better. If you're talking about removing things, then I would talk about it as worse or not worse.
Yes, thank you.
Mm-hmm. So I would say that either the unstructured model is significantly better than random quadratic, or I would say that random quadratic is significantly worse than unstructured. And if it were good enough, they shouldn't be different. Yep. Same idea with the Wald test for the means. Basically, this is, did these three terms help? If the answer is yes, then that means that our model did not do a good enough job recreating the saturated means. Otherwise, they shouldn't have helped. They should have been redundant with the curve we already created. All right. Any other questions before we call it a week, not just a day? No? All right, then you have your formative assessment number 4, I think we're at, out of 7 to work on for Monday. I will let you know when your next homework is available, hopefully within the next couple of days. Let me know if you need anything otherwise, and we'll talk about piecewise models next week. Cool? All right, thanks for being here. Have great weekends.